All right, welcome. Today, we are going to pull back the curtain on a piece of technology you use every single day, but probably never see. We're talking about the internet's invisible backbone, distributed databases.
So let's start with a question. Just think about this for a sec. It's Friday night. You, your friends, somebody in Seoul, and somebody else in Sao Paulo all decide to hit play on the same new movie at the exact same time. How? How does that even work without the whole system just, collapsing?
Because this isn't just some little puzzle for Netflix. It is a massive, massive technical problem that really defines our entire modern internet. Being able to deliver a perfect, instant experience to literally everyone, everywhere, all at once, well, that's the holy grail.
And it's not just for streaming movies. Every single time you check your Gmail, or you buy something on Amazon, or you scroll through your Google Photos, or even just check your bank account, you're relying on a system that has to solve this exact same problem. It has to give you your data instantly, no matter where you are.
So, what's the secret sauce? How do they pull it off? Well, the answer lies in this really brilliant idea. Instead of having one giant central computer trying to do everything, you have lots of smaller ones, all working together. So, the official definition goes something like this. It's a bunch of databases that are physically spread all over the place. We're talking different cities, different countries, different continents. But to you, the user, it just looks and feels like one single unified database. Maybe the best way to picture it is with a library. Imagine you could walk into any branch of your local library, and their computer system knows exactly what books are at every other branch in real time. The books are spread out, sure, but the information, that catalog, is totally unified. That's the magic trick here. Okay, so now that we get the basic idea, let's look at the two main ways engineers actually build these things. Because, the path they choose makes a huge difference. So on one side, you have what's called a homogeneous system. Just think, all the same. Every single computer in the network runs the exact same software, same operating system, everything. It's way, way simpler to manage. But then you have heterogeneous systems. This is more of a mix and match approach. Different locations can use totally different software. It's a lot more complicated to run for sure, but it gives companies this incredible flexibility to use the best tool for the job in each location. So you might be asking, why would anyone go through all this trouble? Why build these incredibly complex, globe-spanning systems? Well, the answer is that the benefits are so huge, they're basically the reason our digital world even works.
First up, reliability. If a server in, say, London suddenly goes offline, another one in Paris or Berlin just picks up the slack instantly. You, the user, never even notice. Then there's performance. Things just get faster. Because if you're in Tokyo, you're grabbing your data from a server in Asia, not one that's all the way across the ocean in California. And the big one, scalability. If you need more power, you don't have to build a bigger, badder supercomputer. Nope. You just add more regular computers to the network. It's that simple.
And to really put that scalability thing into perspective, get this. We're not talking about thousands of interactions or even millions. Netflix uses a system like this to handle billions of customer interactions, clicks, plays, searches, you name it, every single day all across the planet. That's a scale that is it's physically impossible with an old school traditional database. And the advantages just keep coming. It's actually cheaper to keep data close to where it's being used instead of constantly shipping it around the world. You can add new features or whole new servers without ever having to shut the service down. And because your data is copied in a bunch of different places, if there's a disaster, getting everything back up and running is so much easier. Okay, but it can't all be sunshine and roses, right? Of course not. All of this power doesn't come for free. Building and running these systems comes with its own set of pretty major challenges. For one, these things are incredibly complex to manage. You need more hardware, more complicated networks, and highly specialized, very expensive staff to run them. From a security standpoint, having all these different access points means there are just more doors for attackers to try and pick. And the whole system, the entire thing, is completely dependent on having fast, stable network connections between all the parts. But the single biggest problem, the one that keeps engineers up at night, is consistency. Think about it. If you update your bank balance in one location, how do you make absolutely, positively sure that change shows up everywhere else in the world, instantly and perfectly? That puzzle, that's the real challenge. In fact, this problem is so fundamental, there's a famous rule in computer science called the CAP theorem.
It basically says you can have three things: C for consistency, where everyone sees the same data; A for availability, where the system is always online; and P for partition tolerance, meaning it keeps working even if the network breaks. The theorem says you can pick any two of those, but you can never have all three at the same time. You're forced to make a trade-off.
So, let's zoom back out for the big picture here. When you put all the pieces together, the incredible power and the mind-bending complexity, you really start to see just how important this technology is. I mean, they're not just some neat tool for tech companies. They are the essential hidden foundation that powers pretty much everything: global finance, social media, online shopping, all of it. This is the technology that lets us live and work in a truly interconnected world. And that brings us to a final thought. We know these systems
As
are
our
what make our
world gets
world
more
work today,
connected,
but the
what
demands are only
challenges
getting
come
bigger.
next?
We're connecting more devices, generating just insane amounts of data. So what
As
comes
our
next?
world gets more
What's the
connected,
next big data
what
challenge
challenges
waiting
come
for us
next?
just over the horizon? The one that's going to require a totally new way of thinking.